Dear students, now in physics, let's see another experiment within the section mechanics. This is about finding the relative density, right? We have done few different experiments on the same subject matter, finding relative density. Here what we are going to use, a small bottle known as density bottle. I'll tell you later why we call it density bottle, what's the speciality of this bottle, right? This is how it will look like, we'll come to that, density bottle. That's one part of this experiment. You can use the density bottle, find the density of oil, any other liquids, even solids which are in small particles, for example sand. We can use this density bottle and find the density of sand. That's what we are going to see in the first part of this experiment. And then in the second part of the experiment, as a continuation of this, we will see how we can use a test tube or boiling tube. We call it weighted boiling tube or weighted test tube to find the density or relative density of liquids. We are going to see all of that now, right? So first let's start with the density bottle experiment. Look at this. This is how the cross section will look like, density bottle. It's a small one. When I do the experiment, I will show you. It's a very small one, like 20 milliliter, 25 milliliter capacity. A small bottle. And what you see here is the cap of it. That is also a glass gap. The wall here will be thin wall, and the cap of it will have very thick walls. The important feature, can you see, there is a small capillary hall here, right? In the cap also there is a capillary hall. So what's the purpose of this capillary hall? Now let me explain one thing to you. Okay, now this is what we are going to do. What we are going to do, the relative density can be written as mass of whatever the liquid or that material, mass of that substance divided by mass of water with the same volume as of liquid, same volume. This is what the idea we are going to use. If you ask me how this formula has come, you know relative density can be written as density of that particular liquid, let's say, okay, dl divided by dw. It can be liquid, solid or whatever. Density of that substance divided by density of water is what you call relative density. So, dl over dw. Now, let me multiply this by same volume up and down, v. Nothing wrong, right? You can multiply a fraction up and down by same variable. Now, what is this? Volume into density is mass. Mass of liquid divided by, this is mass of water. But must be of the same volume. Same volume, you find the mass of liquid, you find the mass of water divided, that should give you the relative density. For that only we are going to use this bottle. Hold on. If we don't have the bottle, what would we do? Okay, you have a beaker. Take this beaker, first you fill this with particular liquid, say coconut oil, fill this with coconut oil. You can get M liquid. Take it again, clean it, you can remove the coconut oil, wipe it, clean it, fill it with water again, find MW, get the ratio. But that method has an error in it. I'll tell you what is the error in using the beaker for this. The liquid columns, if you take the beaker, the liquid here, it won't be flat. The top surface of the liquid will not be flat. It will take a shape like this. We call it a meniscus. You remember we studied this. We will study more about that in the lesson known as properties of matter. There is another lesson towards the end of your syllabus. Properties of matter, that is where we will study more about surface tension. Liquids have a property known as surface tension, right? The molecules in the surface, they pull each other, they are connected to each other. Because of that, there is something called surface tension. So what will happen? These molecules will go and drag that wall as well. Because of that it will have a curve. So it is not going to be flat. So what? That curve depends on the type of liquid. That means the curvature of water column, curvature of oil column will not be same. Will not be same. Look at this. Look at this. Let me draw that bigger. Let me zoom this and let me draw it big for you. Say that's the beaker. That's a beaker. Right, that's your beaker. The top surface, that's the top surface, but the water level, water will not be like that. See, I'll draw the water with, let's say, I'll draw with black color. Black color. If this is the water surface, when you pour the oil into it, the curvature of oil or whatever the liquid, depending on the nature of the liquid, it can be coconut oil, engine oil or kerosene or whatever the oil or some other liquid, some sulfuric acid, something else. You want to find the density of another liquid, right? Forget about oil. So, the other liquid, assume the curvature of that is going to be like this, the other liquid. Then, when you measure the mass of them, do you understand you are not measuring the same volume? Why? Water was up to this level, even though you filled it to the brim, like when you look at it with your bare eyes, it looks like it's up to the brim. But actually, water had a curvature up to here. The other liquid is if the other liquid is having the curvature up to here, in terms of volume, there is a difference. How much is the difference? See, this gap is the difference. So, when you apply in the equation mass of liquid divided by mass of water with the same volume, it's not the same volume you are using. It's slightly different. This is the problem in using beaker for this experiment. Beaker or anything else with a wide opening, this issue is going to be there. I said wide opening. What happens if it is a narrow opening? Something like a capillary tube, if it is there, think if you have a narrow tube, then the curvature can be neglected because it's very narrow, right? Say even here, if you take a narrow segment, okay, the curvature is going to be very small. Still, there can be a small gap between the water column's curvature and the other liquid's curvature. But since the cross section is too narrow, the curvature's differences can be neglected. If curvature's differences can be neglected, you can see that, right? It's a capillary tube I am talking about, very narrow opening. Then the curvature for water, curvature for liquid will be more or less same. The difference can be very, very, very small, right? That's why we take this bottle, right? So, what do we do here? See, this is how we do the experiment. First, you take empty bottle and measure the mass of it. Then, fill this with water and get the mass of it. So, M2 minus M1 will be water. Agree? Why? M1 is only the bottle. M2 is bottle plus water. So, water M2 minus M1. Then what you do? Fill this with oil. Remove the water. Dry this bottle. Make sure you dry it. There is no water particles in it. Then you fill it with oil, get the mass of it, M3. So, M3 minus M1 would give you the oil or the other liquid, M3 minus M1. When you are filling also, this is how we fill it. See, your bottle is going to have a shape like this, right? What do? You fill up to here. Entire thing you fill. Then you are going to push the cap inside that. When you push the cap, see, let me draw the cap on top of that. The cap will take a shape like this. This is how the cap is usually. So, when you push the cap, this much of water has to be displaced, right? Because cap needs space to come in. That water would go through the capillary hall in the middle. There was a capillary hall in the middle, right? Right. Through this capillary hall, that excess water will come and will go out. So, once you pushed it in, once you have closed it with the lid or the cap, then you can see the water level would have come all the way, like you have water everywhere, and even here you will have water up to here, up to here. Understand? That's how we fill it. Oil also do the same way, so that now you can confirm, okay, the volume of water, volume of oil are same. Then only we can take the mass to mass ratio and say that's the relative density. Understood? Right. That's what about oil. Now let's see how do we do it for sand. Sand, we have a complication. I'll tell you why. If you take sand and when you fill this bottle with sand, okay, say this is the bottle. Right. When you fill this with sand, what happens is the sand particles are particles like this. Maybe in irregular shapes, but they are particles. When you zoom and see, they are big particles, not like water. Water molecules, water particles won't leave space in between. But sand particles, since the particles are big, there is going to be space. I will show you where. Look at this. This is an empty space. 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 There is going to be empty spaces in between the sand particles. Therefore, if you just fill this bottle with sand, it doesn't mean you have occupied 100% volume of that bottle. No. Because some percentage, see, like there is a past paper question also, we will do that later. If you take a box and if you fill it with balls, say footballs, okay, if you have kept footballs like this doesn't fully occupy the space of this box. You can see spaces are there in between. Understand? So, that since the balls are very big, you can observe that with your bare eyes. Sand particles are small, so the gaps between or gaps among the sand particles you can't observe with your bare eyes because that's too small. But still there is going to be gap there. Right? So, you can't say if you fill this and measure the weight and say, okay, I have got the same volume of water and same volume of sand. Wrong. Because this sand did not fill the bottle 100%. Even though it has come up to the brim, it doesn't fill it 100% because in between there would be spaces. In between there would be spaces. So, how do we do experiment for sand? Look at this. M1 is there, empty bottle. What is M1? Empty bottle. Right. M2 is there, bottle plus water. Water for the full bottle, full capacity. So, let me call it V. V. Volume V. Water's volume V. M3 was about the oil, leave that. M4, you fill it like this with what? With the sand, you fill it. Fill it as much as you can or even to half of it, whatever. fill certain volume of sand and get the weight of it. M4 bottle plus sand. But this sand is not the same volume as of water. Even if you fill it up to the brim, it can't be counted as the same volume because there will be gaps in between the sand particles. Therefore, let me call it V naught. V naught. Right. Then if you subtract M4 and M2, M4 and M1, you know that's the mass of sand. Mass of sand. Now the problem is I need to get the same volume of water. How do I get same volume of water? Simple. Okay, let's say this bottle, let me redraw it. Let's say you have sand only up to this much. This is sand. So this is what V naught is. Now fill this, the excess space you have there, fill that with water. Right? So water is going to go in and water will fill it. So bottle and the sand you already filled, now you are filling water with all that, the weight or mass, let's say M5. Bottle, water and sand. Now this time tell me, sand, it's the same volume that was there, right? Can you tell me the excess water you have put in there, how much is the volume of that? What is the volume of that? Is it V? No, V is the full bottle volume. This time we are not filling full bottle because sand is already in. So the remaining space only the water is going to fill. V is the total volume. Of the total volume, V naught was already occupied by sand. V naught was already occupied by sand. The balance is water. V is the full bottle size. V naught is the sand in that. The balance has been filled by water. So now water that you have used is V minus V naught. Right. Now I need to get the same volume. This is for M4 minus M1 is the mass of sand, volume V naught, right? Now let's say V naught volume, water mass. How do I get that? Because then only I can divide these two. V naught volume, sand mass is this. So V naught volume, water mass has to be taken. How do we take that? Look at this. Look at it. If you take M3 minus M2 minus M1, M2 minus M1, let me write it somewhere else. If you take M2 minus M1, that is the V volume, water mass, correct? M1 is the empty bottle, M2 is the V volume, full volume. So that's V volume, water mass. Subtract these two, M5 minus M4. What is M5 minus M4? M5 minus M4, look at this carefully. This is bottle and sand, this is bottle, sand plus water. So the excess water we have used. How much is the water we have used? V minus V naught. So this is going to give us V minus V naught volume, water mass, isn't it? Because what is the extra between M4 and M5? It's this water only. So M4 to M5, whatever the extra mass we have got is of that water. And what's the volume of that water? It's V minus V naught. Why? V is the full volume, V naught already sand is there, balance is V minus V naught. So V minus V naught volume is given by M5 minus M4. So if V volume is M2 minus M1, V minus V naught volume is this. How do we get V naught volume? If you subtract these two, M2 minus M1, that is full water mass, minus M5 minus M4. right, V volume. From that you are subtracting V minus V naught volume. So, V and V will be cancelled, V naught will remain. So, the difference between these two must give you V naught volume water's mass. V naught volume sand mass is M4 minus M1. Same volume water is given by this one. Get the ratio between those two. That should give you the relative density of sand. Clear? So, this is what the concept is. Density bottle can be used for liquids. It can be used for small particles like sand as well. Right. Let us see now the principle. Relative density of a substance is dl over dw. dl is the density of that substance, dw is the density of water. Multiply this equation by a certain volume up and down. Multiply by V and V. Now, you get dl into V is mass of that substance divided by mass of water with the same volume. Mass over mass. Volume has to be same. Materials. Density bottle, water, coconut oil, sand. Triple beam balance to get the weights, masses, to measure the masses. Triple beam balance. Method. Measure the mass of empty density bottle M1. Fill the bottle fully with water and find the mass of the bottle with water M2. Remove the water, dry the bottle, fill it with coconut oil and measure the mass of the bottle with coconut oil M3. Mass of coconut oil is M3 minus M1. Mass of water with the same volume is M2 minus M1. Relative density has to be M3 minus M2 minus M. So, this is an additional calculation. When you say method or the steps, procedures, you don't have to write this. First step, second step, third step. Move on to sand. Remove the coconut oil from the bottle, dry it, fill it with sand and measure the mass of the bottle with sand, M4. Top up the bottle with, that means with whatever was already there, now you fill some extra water in it. Top up the bottle with water and measure the mass of bottle, sand and water and call it M5. So, mass of sand is M4 minus M1. Mass of water with the same volume, I already explained, M3 minus M1 minus M5 minus M4, I already explained how it has come. Get the ratio between those two, that will give you the relative density of sand. So, you can use this for even small particles like say like wooden powder, or let us say the lead shots we use, small balls like metallic balls that we use as in the wheels we keep it for like lubricants. Yes. So, you can use lead shots, small metal pieces, all that you can use this method to find. As long as you can put that in the density bottle, because density bottle has a very small opening. Through that opening, whatever you can put in, you can use here and find the relative density. Clear? Right. So, that is what the steps are. Now, let us see how the experiment is going to be. Students, you can see the apparatus and materials I am going to use in this experiment. This is what we call tri-beam balance. Tri-beam balance we call it. There are 3 beams on it. Can you see? This is one beam, this is another and this is another. In the middle beam, you can measure in hundreds, like you have 100 here, 200, 300, 400, 500, up to 500 grams you can measure in the middle one. So, using the middle beam, you find out within which 100 the measurement is going to be, whether it is 0 to 100, 100 to 200, 200 to 300, all that. And then after identifying in which 100 you have the reading, then you adjust here in the top beam, the second beam here, that is in tens of grams. See, 10 gram, 20 gram, 30, 40, 50, 60, 70, 80, 90, 100. So, after identifying which 100 it is, say for example, you have identified the weight to be 100 to 200, then you check whether it is from 100 to 110 or 110 to 120 or 120 to 130. All that you check using this. After identifying which 10 it is, here in this first beam, look at this beam. In this beam, you can adjust gram by gram. You can see 0, 1 gram, 2 gram, 3 gram, likewise it goes. And there each gram is also divided into 10 sections. That means we can measure each 0.1 grams here. The least count of this apparatus is 0.1 gram. So, to the accuracy of 0.1 gram, you can take the measurements using a 3-beam balance that I am showing here. When I take the measurements, I will show you how to use this. Also, you can see here we have 2 lines. So, these 2 lines must be collinear when you balance it. So, we will keep the weight here on this plane and then you adjust these weights. See, this is 100, 200, 300, likewise you can adjust this and then you can adjust this into 30, 40, 50, likewise you can adjust this, and this is a continuous one. You can adjust from 0 to 1 gram, 2 gram, 3 gram, likewise you can adjust this. This is how we adjust it. When we keep the weight here, we adjust these weights and balance these lines. That is what we do with the dry beam balance, right. When I get the measurements, you will understand it better how to use this. And then this is what we call the density bottle. You can see here, density bottle. It is a small bottle with some special features. I will explain the special features. Look at this, it has a lid. It has a lid, right. And on the lid, you have a small hole here. Can you see there is a small hole here? I will show you the hole. See, when I insert this pin through it, it can go. Such a small hole. When I insert the pin, it can go through it. Such a small hole. Let me explain the purpose of this small hole. Why do we have this small hole? You know, if you take a beaker, if you fill it with water, say up to the top level you are filling it with water, the water level will not be flat. You will actually see a small meniscus there, small curvature. And that curvature will be different from liquid to liquid. When you use oil, that curvature will be even bigger than the curvature of water. So, depending on some other features of the liquid, depending on some other characteristics such as viscosity of the liquid, that curvature is going to differ. So, what we are going to do in this experiment, we are trying to find the relative density of a liquid. How are we going to find the relative density? We take this bottle, we first fill this with water and get the weight of it or mass of it. Before that, we should have taken the empty bottle's mass, then you fill that with water and get the mass. If you get the difference between the first and second readings, that will be the mass of the water that you have filled in. Then you remove the water, you clean it and fill the same bottle with oil to the same level. Imagine if you have taken a beaker or some other bottle which has the cross section bigger, then you are going to have that curvature. So, even if you fill it up to the top level of it, since the curvature is going to be different for water and oil, you cannot ensure you have same volume of water and same volume of oil in that bottle. So, how do we avoid that here using this bottle? Since this hole is narrow, we will be filling this from the bottom up to this capillary hole, up to the top of it, we are going to fill it. So, the opening is very narrow, the hole you have here is very narrow. When the cross section of the hole is very narrow, very small, then that curvature will be negligible. Whether it is going to be water, oil or whatever, that curve can be negligible. It is almost flat, it will be there. Therefore, we can ensure that the volume of water that we have used and the volume of oil that we have used will be equal. Right? That is one special feature of this density bottle. Second thing, after filling this with water or oil or some other liquid, we should not hold it from here. We should not hold it from the bottom, because Usually compared to the environment, the body temperature is higher. So, what will happen when you hold it like this, your body temperature will be transferred in and the liquid will get heated and then it gets expanded, right. So, to avoid that, what we should do after filling this with a liquid, we must ensure we always hold it here at this point. Why? At that point, the thickness of the bottle is much bigger. So, the heat from my fingers cannot easily be transferred into the liquid, right. So, that is another feature we have in this density bottle, right. So, that is the special bottle that we use here, known as density bottle in this experiment. We have a beaker of water. I told you we are going to fill this with water, fill the bottle with water and get the mass of it. This is a beaker with oil, coconut oil. We are going to find the relative density of this coconut oil. Also remember, at the beginning I told you we can use this bottle to find the relative density of solid which is in small particles. For that I have taken sand, dry sand I have taken. I am going to find the relative density of this dry sand as well. This is all the materials and apparatus that we need in this experiment. Let us start getting the readings. To find the relative density of oil, what should I do? Let me repeat it. Get the mass of empty density bottle, fill that with water up to the top of that capillary hall and get the mass of it. Clear that, clean it, fill it with oil and get the mass of it. First reading, second reading will give us the mass of water that was filled in. First reading, third reading difference will give us the mass of oil that was used in. Mass of oil and mass of water are for the same volume. Therefore, when I divide it, mass of oil divided by mass of water, that should give me the relative density of oil. So, that is the first part of this experiment. I am going to do it. You need to understand, I have been repeatedly telling this in every experiment. When you use the apparatus, when you use the measuring equipments, the side where there is scale should be on your side. You can't keep it like this and do the experiment, because then you will have to keep the weight here. You have to run to the other side, balance it and get the readings. So, always turn the apparatus, keep it such that the readings, the scales are on your side, right. So, because of that, let me turn this weighing scale, the tri-beam balance, to my side. Right, this way I can see all the readings, it is in my side. Let me keep the empty density bottle and see what is the weight of it, right. Like I mentioned earlier, first let me check in which 100 it is there. 0 to 100, let me increase this. Can you see, when I increase this to 100, this side has gone down, indicator has gone down here, which means the weight of this bottle is less than 100 gram. Bring it back to 0. So, now it is confirmed the weight of this is 0 to 100. Let us identify in which 10 the weight is. Increase this to 10. It is still up, the index or the indicator is up, it is above 0. Let me increase this 20. It started oscillating. Let us give it some time until it remains stable. If it is up, then I'll have to move it further. If it is down, I have to move it back. Let us see where it stops. The indicator is exactly at the same 0 level. The indicator line, the index line and 0 are collinear. That means the weight of this bottle is exactly 20 grams. See, the hundreds, it is in 0. And the ones also I have kept it in 0. Only in this beam we have moved 20 gram. This shows 20 gram and it's balanced, which means the mass of this empty density bottle is 20 grams. What next? I have to fill this with water and see how we fill this. You have to be very careful when you are filling this. Let me fill this with water. Let's fill water into this. I have filled it almost up to the full capacity of this bottle. Now we have to close this. You have to observe carefully. When we close it with the lid, the water will climb up in the capillary hall and it will start coming out from the capillary hall. Right? The extra water we have here will come out through the capillary hall. So you have to observe that carefully, because we have to ensure we have filled water up to the top of that capillary hall. Right? Let's see. I kept the lid, but still the water level has not gone up to the top of the capillary hall. So let me fill some more water and try it again. You can see on the top of this capillary hall, the water bubbles have come out, the water has come out. The excess water you had has come out through the capillary hole. Then I can ensure the water has climbed up all the way to the top, right? Let me take it, and I had to wipe this clearly, because if I keep it like this, the water drops around this also will add to the weight. I should not allow that. I have to ensure only the bottle, the water inside that and the lid are kept here. Let me wipe it all around. Let's get the weight of this now. Let's bring it to 30. More than 30. Bring it to 40. It's more than 40. When I brought it to 50, it has come down. That means it must be less than 50 but more than 40. 40 to 50 is the weight range. Bring it back to 40 here. And let's increase it one by one. 41, 42, 43, 44, we get it exactly at 45 grams. 45 grams, the lines are collinear. That means the mass of this bottle, lid and the water in it all together, it's 45 grams. It is somewhat expected, I'll tell you why. Can you see in the bottle they have printed, the manufacturer has printed, the capacity of this bottle is 25 milliliter. We know density of water is 1000 kilogram per meter cube. That means 1 gram per millimeter, 1 gram per millimeter. So this 25 milliliter should be 25 grams. 25 grams. The empty bottle is already 20 gram. We already measured it, it was 20 gram. So 20 gram of empty bottle plus 25 grams of water in it, altogether 45 grams should be the weight of it, which is confirmed here. I get the reading of 45 grams. So from 45 gram, empty bottle 20 gram, you subtract it, water is 25 gram confirmed. What is the next step? I have to remove this water, I have to clean this, I have to ensure there is no more water in the bottle, I have to dry it, then I have to fill this with oil, coconut oil, and get the mass of it. So, let me clean it, let me dry it and continue the experiment. Children, you can see that I have taken this bottle, I have removed all the water from it and it has been cleaned. There is no more water in it, you have to wipe it and dry it to ensure there is no water drops remaining in that. What am I going to do? Similar way I filled it with water, now I am going to fill it with oil. So, oil has to be filled up to the top of this hole. I have filled it to the top of the bottle. Now, let us close it and see whether the oil fills the hole to the top. You can see from the top also the oil filled and it was coming out of the bottle from the top of this capillary hole. Now, I can wipe it and check whether I have the oil column up to the top of it. Ensure there is no oil around this because that can increase the weight of it. That can be an error in the experiment. Right, I can see the oil column has come up to the top of this hole. So, last time when we filled this bottle with water, the weight of bottle and water was 45 grams. So, this time the weight, what do you expect? Do you think it has to be above 45 or less than 45? It has to be less than 45 grams because same volume of oil, but the density of oil is less. Since the density is less, the weight or the mass has to be less, right. So, let me bring it back to 0 and increase it, right. Empty bottle was 20, so it has to be more than 20. It is more than 30 as well. Can't be much of a difference because water's density is 1000, oil's density approximately is 900, we studied that, right. So, 1000 to 900, there can't be a massive difference in the mass, it is more than 40, but it has to be less than 45, we know that. So, let us increase this one by one, 41, 42, students, it exactly balances at 43 grams, 43 grams it exactly balances, 43 grams, right. That means the bottle, its lid and oil at the same volume of water that we used, it is 43 grams, right. So, let us write down these three readings that we have got now. Empty bottle's weight was 20 grams, bottle with water it was 45 grams, bottle with oil it was 43 grams. Let us write down all these values and see how the calculation is going to be. So, the readings we have got now, M1, let us say the mass of empty bottle and lid, it was 20 grams. Then we measured the bottle with water and lid, let us say M2. It was 45 grams. So, you know the difference between these two, 25 grams is the mass of water. Then we filled it with oil and the measurement was 43 gram. So, 43 gram and the empty bottle 20 gram difference is 23 grams. The mass of oil has to be 23 gram. So, relative density of oil, mass of oil divided by mass of same volume of water, 23 gram divided by 25 gram, right, which comes to approximately 23 by 25 means it's you multiply up and down by 4, it's 0.912, which is very close to the theoretical value we study about coconut oil. We say it's around 900 kilogram per meter cube, the density, which means relative density has to be 0.9. Yes, we have got 0.912. So, that is how you find the relative density of oil. What we are going to do next, remember I told you at the beginning, we can use a similar method to find the relative density of solids which are in small particles. So, let us find the relative density of dry sand that I have shown you now. Now, you can see I have the density bottle cleaned. Now, what are we going to do? We are going to fill this with sand to a certain extent. It does not have to be full because you know sand anyway cannot fill it to the same volume as of water, because water particles, water molecules can fill it fully, whereas sand particles are much bigger than the water molecules. So, in between the sand particles there will be space for sure. So, there is no possibility you can fill this to the same with sand to the same volume of water. You can fill this with oil because that is also a liquid, you can do it, right, but not sand. So, what we will do, we will just fill it to a certain amount, let us say 3/4 of it, we will fill it and get the mass, and then I will tell you the technique we are going to use to find the mass of water of the same volume of sand, right, that we will have a special technique for that. So, let me fill it with sand now. It might be difficult for you to fill this with sand because this hole is small. So, you can use a funnel, using the funnel I can fill it easily. Now, let us get the mass of this bottle, sand and the lid. Let us bring it back to 0. Increase by 100, it is less than 100. Increase 10 by 10, 20, 30, 40, 50. When it is 50, it is higher, which means it has to be in between 40 and 50. Bring it back to 40, 41, 42, 43, 44, 45, 46, 47, 48, 50, It has exactly balanced at 48.6 grams, 48.6 grams, right. So, that is the mass of this bottle lid and the sand in it. Empty bottle and lid, it's 20 gram. So, when we subtract it, we know the mass of sand is 28.6 gram. Now, my next challenge is, how am I going to find the mass of water of the same volume of this sand? Simple, look at this, what we are going to do. The remaining space in this bottle, now we are going to fill it with water. So, imagine if the full capacity of this bottle is V1, V1 volume water we already measured, that was 25 gram. Now, let us say the volume of this sand is V2. When I fill water into this, the water that fills this now has to be V1 minus V2, right? V1 is a full capacity of which up to V2 there is sand. So, the water has to fill V1 minus V2. I can get the mass of it. Why? I know the mass of it now, the system now. Fill this with water and then get the mass of it. So, get the difference between this mass and the mass with water. That has to be the difference between those two, has to be V1 minus V2 volume, water's mass. V1 volume, full volume water, mass has been measured. V1 minus V2 volume, mass is going to be measured. Subtract it, you can get V2 volume mass of water. V2 volume means there's the same volume as of sand. Understood, right? When I do the calculations, I'll explain this once more. So, now what we are going to do, the next step is to fill this bottle with water in the same way we filled earlier, but make sure with the sand. This is why I said, when you are using the solids here, you have to ensure that solid doesn't dissolve in water. If the solid dissolves, then when you put the cap on it, when you put the lid on it, some dissolved solid also might go out. So, we have to use the solids that doesn't dissolve in water, right. So, let us fill this with water now. Filled it fully, let us close it. It hasn't come to the top, we have to fill it again. Now, the water level has gone down, let us try it again. That is right. Now, the water level is up to the top of this capillary hall. Let us wipe it now. All right, now it is all clean, we can get the mass of it now. It has to be more than this 48.6, but I do not know in which tens it is. Let's bring it back to 0. Still it is less than 100. More than 40, more than 50, more than 60 but less than 70. Bring it back to 60. Let us increase one by one now. So, we understand it is in between 60 and 70. Increase one by one. 61, 62, 63, it is more. So, it has to be less than 63. Students, it has balanced at 62.8 grams, 62.8 grams. From this, if you subtract the previous reading we got, which was 48.6, if you subtract that, that has to be the mass of water that we have added. That is 62.8, 48.6, if you subtract it, 14.2. You know, full volume, if it is filled with water, that is 25 gram. This excess water we have filled is 14.2 gram. Subtract it, you get 10.8 gram. What is the 10.8 gram? That is the mass of water which has taken the same space, same volume as of this sand. 10.8 gram is the mass of water which has the same volume as of this sand. We already have measured the mass of sand. You divide mass of sand, divide by the same volume water mass, it has to give you the relative density of sand. Understand? So, this is a simple way you can get the relative density of solid particles, but which has to be small particles which can be filled into this. This is how we measure it. Shall we write down these values as well? M4 we got 48.6. What is this M4? This is the bottle lid and sand in it. So, if you subtract 20 gram from it, that will give us the mass of sand. 48.6, 20, subtract it, you get 28.6 grams mass of sand. Then we got M5, we filled it with water, it was 62.8 grams. Right. So, we subtracted these two to find how much of extra space was filled with water, that is 14.2. Full water volume is 25. So, 25 gram minus this 14.2 gram, 10.8 gram, that is the volume of water. Volume of what? Volume of sand. See, this 10.8 gram is the mass of water which would have had same volume as of sand. Same volume as of sand, 10.8 grams. So, you divide 28.6 by 10.8 grams, you will get the relative density of the sand, dry sand that I have used here, right. So, let us do these calculations and see what relative density we get for this. Right. So, now here you can see the readings that we have got. M1 is only the bottle, right. This is bottle and oil. This is bottle and water, and then this is the bottle and sand. So, M1, M2, M3, the order might change. So, understand carefully what is there in each of them. Bottle, sand and water, right. Okay. Now, let me take the full volume of oil, right, mass of oil. Straight away, let us write density of oil, relative density of oil. You need to take the mass of oil, which will be 43 minus 20, divided by mass of water with the same volume, 45 minus 20. No need to convert that to kilograms and all, because both are gram, it will cancel each other. 23 by 25, 0.92. 0.92, 25 dividing by 25 means multiplying by 4 up and down. Then this will become 100, 92 over 100, 0.92. That's the relative density of oil. We usually assume it to be around 900. Yes, coconut oil, it doesn't have a perfect standard value. Around 900, it can have values. Now, relative density of sand. Get the mass of sand. Bottle plus sand. Bottle, get the difference. 48.6 minus 20. Over, carefully, the mass of water with the same volume. First, we will get the mass of water with the full volume, which is this 25, right? We already found it. Here 45 minus 20, I will write it. So, when you fill it fully, it is this much. After sand is there, to top up how much of water was required, the difference between these two, because this is bottle and sand, this is when we topped up. 62.8 minus 48.6. 28.6 over 25 minus, this has to be 14.2. 28.6, this is 10.8, correct? 286, 108, 2, 216, 700, 6, 46, 4, 2.64, 2.64 is what we get. 28.6 is the mass of sand, 25 minus 14.2, 10.8 is the mass of water with the same volume. So, you get the ratio 2.64. Relative density of sand is 2.64. Clear? So, this is what we call using the density bottle to find the relative density of liquids as well as solids in small particles. Why small particles? You saw that we should be able to fill it within the bottle, otherwise we can't fill it. Right. So, that is all about the first part of this experiment. Now, let us continue the experiment. You remember I told you there is another part in this experiment where we are going to use a boiling tube. We call it a weighted boiling tube. I will explain why. Using the weighted boiling tube, how to find the relative density of liquids. This method is particularly for liquids only, right? Look at this. Determination of the density of a liquid using a weighted test tube. Weighted test tube, or you can say weighted boiling tube. You take a test tube and we have to immerse it in water such that it remains vertical in water. So, usually if you just take a test tube, it does not remain like that. It will be just floating in all the directions. It will not be stable. So, to make it stable and vertical, we do a thing. What do we do here? We put some weights to the bottom of it, some heavy weight. Heavy in the sense relatively heavy. What we usually do, we bring some lead shots. Lead is metal, you know that, lead shots. That means small balls basically. Small balls of metal, you put it there. Carefully you have to put it, otherwise if you put it faster, it might break the glass. The test tube will be damaged. So, carefully you put few metallic balls which will be heavy, and then you just seal it. How do you seal it? You can pour some wax into it, heat the wax and pour it into that, so that the bottom will be sealed. Right? There are two advantages of doing this. Main advantage, or one of the advantages, right, now the center of gravity would have come down because you have put more weight here. So, when you put it vertically in water, it remains vertical, it floats, part of it immersed, part of it out, it floats, but vertically it floats. That is first thing. Second thing, when we talk about the volume of this test tube, now see, above this point, from here to here, right, this much, volume will be area into length, because area cross section is uniform. Cross section is uniform. But this part, the cross section is not uniform, right? Cross section reduces and you don't see a format there, right? So we are going to do some calculations where the volume will be required, right? Therefore, we are going to seal this area. There are two advantages. When I do calculations, I will show it again why it is an advantage. One is like by putting this weight, the test tube will remain vertical and stable. Second one, the curved or irregular cross-sectional area with irregular cross-section is covered with wax. What is open after that is the area with cross-section, the volume with regular cross-section only, the volume with regular cross-section. Then what you do, you have to put some scales here. So how we normally do scaling it, you take a graph sheet or you take a paper, you print all the scales like 15 centimeter scale as if in the ruler, like this you print it, cut it into a small strip, paste that strip inside in the inner wall of the test tube or boiling tube, right, so that the scales are visible to the other side, outside. Paste it inside. And where should be 0? 0 should be right there with this wax level. With the level of wax, 0 starts. 1, 2, 3, likewise it increases. Paste the scale like that. Then we put it in the a jar with water, so it remains like this. Then what we do, we add some weights into this, some known weights. Let's say you are adding a 5 gram weight, another 5 gram weight. Likewise, you can slowly, carefully keep some weights inside. If you think if you drop the weight, it's going to break, maybe with the help of a string, you can carefully keep it inside. Right? Okay. Then with the weight also, it will be still floating. Let's come to an equation how it floats. When it is floating, tell me what are the downward forces acting on this test tube and its contents? It's the weight of everything, right? So let me define certain terms here. It is defined here, you can see. M, mass of the tube with its contents. V is the volume of the portion in the tube filled with wax. This black color area I have marked here, let it be V. A, external area of the cross section of the cylindrical portion of the tube. That means above this line, the cylindrical portion is the uniform portion that has a cross section A, external cross section. I'll explain why external, why not internal, wait for that. Mass of additional weights inserted into the tube. Just now I told you we will put some extra weights into that. So that extra weights added is simple M. Rho is the density of this liquid, the one which is outside. We are going to do this experiment for water, but you can do it for any liquid, right? So we will generalize it saying liquid. L is the length of cylindrical portion immersed in the liquid when the tube floats. See, L is this much. This is L. This is L. Right. Now let me write a formula. Look at this. Weight is the downward force. Upthrust is the upward force. There will be an upthrust, right? You immerse anything into a liquid, there will be upthrust. Since weight and upthrust are equal only, it's floating. If weight is more, then it will not remain floating. It will fall. It will reach the bottom of the surface. Right? How can I write the weight? M and M only. Extra weight we added is simple M. The tube and the weight and all those existing contents capital M. So I can write weight to be capital M plus simple M G. Upthrust, what's the formula? Weight of the liquid that has been displaced. Weight of liquid displaced. So let's first find the volume that has been displaced. Displaced volume means, look at this. This is the displaced volume, right? How much of test tube is immersed. If you can find the volume of test tube that has been immersed, that gives you the volume that has been displaced. This black part is V plus the cylindrical part which is immersed inside, cross section A into L. That is the volume that has been immersed, correct? But I need the weight of water, weight of liquid that has been displaced. So, this is the volume, you multiply by density, you get mass, and you multiply by G, that will give you gravitational G. G is gravitational acceleration. So, volume into density is mass, mass into G is going to give you the weight. Density is rho G. Cancel G both sides and divide by rho on this side, M over rho, simple M over rho, V plus AL. Make L the subject of it. Make L the subject of it. I will write this one first. 1 over A rho into M. Then everything we can write plus 1 over A capital M over rho minus V. Bring this V in this side. So, M over rho minus V, both have to be divided by A. So, 1 over A. Now, we can draw a graph Y, M, X, C. Because simple M is something I can change. Simple M is what? The additional weight that we have inserted. So, I can put a 5 gram, another 5 gram, another 5 gram, another 5 gram, I can keep putting weights into that little by little. I can't all of a sudden put 50 grams, 100 grams into that, because then the displaced volume will not be enough. The entire test tube might go underwater, right? It might sink. So, to avoid that, you have to put small weights, 2 grams, 3 grams, put like that, get 5, 6 different values for M, and each time the length is going to change. How much of length is immersed inside, that will change. You put more and more weight, it sinks more and more, right? So, the length changes. All others are constants. A is the cross section. Why external cross section? You are talking about displaced water, not how much capacity inside the test tube. We need to know how much of water has been displaced. Therefore, the external volume is what matters to us, external volume. A, rho is density of this liquid, M is the test tube and the weight we already fixed inside, so that doesn't change. V is the volume of this part under here, all that remains constant. So, this is the intercept and this is the gradient. You take multiple M values, L values, draw the graph. From the graph you get the gradient. Gradient is going to be one over A rho. From the graph you can get the gradient. Where do you get A from? You get A, you have to measure the diameter, external diameter of this test tube. What can we use? What measuring equipment, measuring instrument we can use here? The vernier caliper is suitable. We have even done an experiment with vernier caliper. I showed you how to measure the external diameter of a test tube. You can use the external jaws, fix it and find it. But there is a method for that. How do we find it? You take one point. At that point, say if this is the test tube, you take one point, keep the jaws like this and find the measurement. Again, perpendicular direction, keep it and find the measurement. Get the average, that's the diameter at this point. Don't complete. Go to another point. One reading, another reading. Get the average. Likewise, in 2 or 3 different points of test tube, each you take 2 readings, one and another one perpendicular to that. So, get all those readings, get the average. Somehow you get an average diameter of the test tube. Using that, you can find the cross-sectional area of test tube. Gradient you can get from the graph. Using those, you can find rho, the density of liquid, we can find it like that. Clear? Right. So, that's what the idea is. Now, let's see. According to the principle of flotation, weight of the system, upthrust on the system must be equal. So, this is what I have shown you now. The gradient of the graph M versus L give 1 over A rho. Rho can be found by measuring the external diameter of the tube to find A. So, you measure the external diameter, find A, get the gradient. Using all that, you can find rho. Materials and apparatus, a boiling tube, a tall jar, few mass units, a vernier caliper, a graph paper stripped marked in millimeters. That's the, the centimeter scale that we are going to put inside. So, it can be a graph paper or you can even take it printed. Water, lead shots or small iron balls. Small iron balls is what we use as in the bicycle wheels, we use those small balls. A small quantity of wax. So, I have explained you the purpose of all of them. The method. Put the minimum amount of lead shots that would make the boiling tube float vertically in the liquid. Pour wax into the tube until the lead shots are completely covered. The spherical portion of the tube should be filled with wax. Paste the paper strip on the inner wall so that the zero of the scale begins from the lower end of the cylindrical portion. Fill the tall jar with water because we are going to find the density of water in our experience. So, if it is water, it's water. If it is some other liquid, that liquid has to be filled in the jar. Make the tube float vertically in it and record the length L of the tube immersed in liquid. That means, before you add any additional weight, you can get the length, that will be L. Insert one mass unit into the tube and record the corresponding L value. Increase M and obtain about 5 values, record the readings. Measure the external diameter of the tube using a vernier caliper at 3 different places of the tube, taking 3 readings normal to each other. Right. So, get those values, that will give you the diameter. Right. So, you already have the graph points, draw the graph. It has to be a straight line, not through origin, because with an intercept. So, you draw the straight line, find the gradient and diameter is there, use the diameter, find rho. Gradient equals 1 over A rho. Remember? Come, now let us see how we can do this experiment. Students, as a continuation of this experiment, let me show you another simple experiment that we can do. Right? We have studied about Archimedes' principle, we have studied about upthrust. What did we study about upthrust? Upthrust will be equal to the weight of liquid that has been displaced. Let us say you are submerging a solid into a liquid. It can be water, it can be an oil, it can be anything. Then there is going to be an upthrust, a force given by the liquid vertically upwards on the submerged substance. And that upthrust is equal to the weight of liquid that has been displaced. Using that concept, we are going to calculate the density of the liquid. Right. So, in this experiment, I will show you using the same concept how we can find the density of water. But not only for water, you can do this experiment for even other liquids like coconut oil, engine oil, you can use it for different liquids like that. Right. So, look at the materials and apparatus that I am going to use for this experiment. We need a test tube. Here I am showing you 2 test tubes, but actually one is enough. And then a beaker with water, a beaker filled with water. And then we need small weights. So, I have taken the lead shots here, small like spherical shaped metallic balls, we call them lead shots. So, I have taken lead shots, each 1 gram. It can be 1 gram, 2 gram, 3 gram, some small weights. That is all you need for this experiment. What we are going to do, look at the concept. First, we will put this test tube inside the water. But what will happen, this test tube has very less weight and the center of gravity is going to be somewhere in the middle. The upthrust is also somewhere in the middle. So, then what will happen, when you keep it in the water, it might not come to a stability. It might be, it might not stay vertical. So to keep it vertical when it is submerged in water, what we will do, we will add some weight to the bottom of it. Right? Usually you can add some sand into that. If not, we can put some metallic balls, the lead shots in that. But to fix it, we can add some wax into that and we can fix it there. After you add the weight, the surface has to be horizontal there. Right? We can do that. That's what I have done in this test tube. You can see here, in the bottom of this, I have added some lead shots, basically some weights, and then I have sealed it with wax. And the surface is almost horizontal on top of it. Another advantage of doing this, why we are adding weight to the bottom, the cross section of this test tube is uniform up to a point. Close to the bottom part of it, it's curved. So here, close to the bottom of it, the cross section is not uniform. So to cover that cross section which is not uniform, I am using this weight. Now, I have put a scale also. I have stuck a scale here. You can see that it starts from 0. Where does the 0 start? Exactly at the point where the wax finishes. The weight and the wax finishes. From that point, I am starting a scale. And you can notice that from the point I started scale up to the top of it, the cross section is same cross section you have, uniform cross section you have. Right? Because when we say the displaced volume, I am going to take the cross section A and multiply by H. So when I do it at different points, that A has to be same. If the cross section is different, then that will complicate our calculations. Not that we cannot do, we still can do it, but that will add some additional working in the calculations. To ensure that we have same cross section throughout the scale, I have done this. Right? So after adding the weight, when you keep it in the water, when you submerge it in the water, it almost stays vertical. You can see that. It almost stays vertical. Right? Now, if I look at this scale, approximately 8.5 or 8.6 centimeter it shows. So what is this 8.6 centimeter? Now the test tube and its contents have a weight. And that weight has been balanced by the upthrust. It doesn't touch the bottom of the beaker. So how does this test tube and its contents remain in balance, remain in equilibrium? The upthrust had been equal to the weight. Right? How did the upthrust came? Because part of this test tube is submerged in the water, it has displaced some water. When you submerge something into liquid, it displaces same volume of that liquid, right? That's what Archimedes found out. Right? That's what Archimedes found out. Right? So to balance the weight of this test tube and its contents right now, it has displaced some water. That is at 8.5 or 8.6 centimeter. I think it is at 8.6 centimeters. It's at 8.6 centimeters. Now, what am I going to do here? I'll add some weight into this. Right? Let's say I'm adding 5 grams of weight. Let's assume so. Then when you add weight into this, 5 gram extra you have added, then the test tube will go further down. From this height, let's say this is H naught, from this height, a little more height will get submerged. Let's say the additional height that got submerged is H, simple H. Then I can say the additional weight that I added should be equal to the additional upthrust that it has got. If it is in equilibrium, we can say that additional weight and additional upthrust must be equal to maintain the equilibrium. Additional weight I have added is 5 grams. So 5 by 1000 in kilograms multiplied by gravitational acceleration g, basically mg, that's the additional weight we have added. What would be the upthrust, additional upthrust? Cross section A into the additional height or additional length that has got submerged. A into H, because that's the volume that has been displaced further. AH into rho of this liquid, density of this liquid into G. AH rho G on one side of the equation, mg on another side of the equation. You cancel G and G, you get AH rho equals m. M is a known weight. I am adding known weights here. A can be measured. I have shown in the previous experiments when I introduced you vernier caliper, how to use vernier caliper and find the diameter of test tubes. I have shown that. So, using those techniques, we can find the cross section. You find the diameter and then find the cross section. So, A is known, H is known. That is why we have this scale. So, we can find out how much extra length gets submerged. H is known. On the other side, M is known. AH rho equals M. AH M known. Only rho is going to be the unknown. You can find it. Right. But in physics, what we usually do, we usually go for a graphical method to improve the accuracy of the answer. We don't conclude with one answer, with one reading. We take 4 or 5 different readings and we go for a graph. From the graph, we derive the answer so that the answer will be more reliable. Therefore, even here, I am going to add different weights and get 4 or 5 different readings. Readings of what? H. Right? M and H readings. We will get 4 or 5 pairs of readings. With those readings, we can draw the graph from the gradient of the graph, and with the cross section of this test tube, I will be able to find rho. That's what the very simple concept of this experiment. Right? So, without any additional weight being added, the reading is at 8.6. Now, I am going to add weight into this. I am going to add 3 gram by 3 gram and get weights. Already 0 grams, 8.6 centimeter. Let me add 3 by 3, get 4 more readings, then we can draw the graph. Right? Let me add 3 grams. These lead shots, each 1 gram. Each lead shot is 1 gram. So, I am going to add 3 lead shots into this. We get a reading of 9.2 centimeters now. Without any weight, it was at 8.6 centimeter. After adding 3 grams of weight into it, now it's 9.2 centimeters that we get. Let's add another 3 grams and get another reading. Now, it is at 9.9 grams. Make sure when you are getting the readings, the test tube does not touch the wall of this beaker, because when it touches the wall of the beaker, there can be other forces. And also the water level might not be the same. When it touches the surface, because of the surface tension, there is something called surface tension of liquids. The water level might go up. So, when you are getting the reading, you have to ensure the test tube does not touch the walls of this beaker, right? So, such that now the next reading I have got is 9.9 centimeters. Without any weight, it was 8.6. 3 gram added, 9.2. Another 3 gram added, we got 9.9 centimeters. Let's add another 3, another 3. It is exactly at 10.5 centimeters, 10.5 centimeters, 8.6, 9.2, 9.9 and 10.5 centimeter. Let's get one more reading, then we'll have 5 readings altogether. We will be able to draw the graph. Take the next reading, add 3 lead shots, which is 3 grams. This time it is at 11.2 grams, 11.2 grams, 11.2 centimeters rather, 11.2 centimeters, 8.6, 9.2, 9.9, 10.5 and 11.2 centimeters are the readings we have got when I added 3 gram in each instance. Let's take all these readings, let's draw a graph. We have to get a straight line, we have to get a straight line. From the gradient of the straight line, we need to find the density of water. Also, I have already shown in the vernier caliper experiment, or how to, in introducing vernier caliper, how to find the diameter of test tubes. So, I am going to use those mechanisms, or I am going to use those techniques, find the diameter so that I can find the cross section of this test tube. Then I will need A as well, because the gradient is going to be 1 by A rho, 1 over A rho. Right, draw the graph, measure the gradient and find A as well. Then gradient equals 1 over A rho. From that I can find rho, the density of water. Clear? Very simple experiment it is. Not only for water, you can do this for any liquid. As I mentioned earlier, it can be coconut oil, engine oil or anything. But only thing you have to understand, when the density reduces, every time you add weight, it has to submerge more length to get that volume, because V rho G, if rho is less, V has to be higher. Right, say here approximately every time I added 3 grams, 0.6 or 0.7 centimeters it went down, right. If you do the same experiment in oil, if you add 0.3 grams or 3 grams rather, if you add 3 grams, it might go down by more than 0.6 centimeters. Why? The density of oil is much less than water. So sometimes if the liquid has very low density, you might need a lengthier test tube to do this experiment. So have that in mind, or else you can change the weight that you are adding. Rather than adding 3 grams, maybe you can add 2 gram by 2 gram and get the readings, or 1 gram by 1 gram and get the readings. So you have to be just mindful about those factors when you are doing this experiment. Right? So let's take these readings, draw the graph and see what answer we are getting for the density of water. Right. So you can see the readings that we have got here. M 3, 6, 9, 12 grams and L, the centimeters we have got are these. External diameter of the tube is 2.39 centimeter. Maybe I can find the area of it first. Area pi r squared d by 2 squared. 22.7 or 22 by 7 into, this is 2.39, right. So d by 2 means 1.195, correct, into 1.195. We will divide by 7, 0.171, 0.170707, it goes like that. So I took it as 1.0171. So it will be, when you multiply by 22, 1195, 22, 10, 9, 2, 3, same thing will come, another 2, 2390, 09262, 3 decimal, 26.290, and that has to be multiplied by this now. 2629 into 171. 2629 63 6 14 and 6 22 42 plus 2 44 4 14 8 2629 9 5 6 9 and then 14 4. How many decimals? 2 here, 3 here, 5. 2 4 5. 4.49659. I can take it as 4.5 centimeter squared. Centimeter squared. That's 4.5 into 10 to the power minus 4 meter squared, because 1 centimeter means 10 to the power minus 2 meters. 1 centimeter is 10 to the power minus 2 meter. So, centimeter squared 10 to the power minus 2 squared, which is 10 to the power minus 4. Let's draw the graph now. Right. X-axis has to be M, that goes up to 12. That goes up to 12. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Likewise it goes, right? So, we will take 2 by 2. Yeah, that should be enough. So, let's say 2, 4, 6, 8, 10 and 12. Or we could have even take up to 24. In that case, we will extend the line a little bit. L centimeter, not L, M grams. We will take 2 here, 4, 6, 8, 10, 12. Correct? And then we need up to 11.2. We don't have to start at 0 because we just need the gradient only. Even intercept we know when this was 0, L was 8.6, right? To show, if you want, you can start from 8.6 up to 11.2. So, let me put 8.6 here. We will just put a zigzag here to say that we are not starting from 0. So, let me delete 0. So, even 0 is okay because after that, look at this. We will mark like this. 0 here. This is for the x-axis. Here you put a zigzag and mark this as 8.6. Then you need up to 11.2. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 11.2 means I need another 2.6. 2.6. So, let's take 13 and mark it as, so look at this, I will mark this as 9, 9.4, I am increasing 0.4 by 0.4. 9.8, this will be 10.2, 10.6, 11, 11.4. This is L in centimeters. Mark the points. First one, 3 and 9.2. 3 and 9.2. 3 and 9.2 here. Next one, 6 and 9.9. 6 and 9.9. 6 and 9.9. Here. Next, 9 and 10.5. 9 and 10.5. 10.2. 10. Oh wait, this is 9.2 is correct. 6 and 9.9 is wrong. 9.9, this is 9.8, 10, 9.9 has to be in the middle. 6, 9.9 here. Next one, 9 and 10.5. 9 and 10.5. 10.2, 10.4, 9 and 10.5 here. Correct? 12 and 11.2. 11.2 is going to be here. 12. This is 9. Yeah, this is 12. 12, 11.2. Right. Can see almost a straight line we can see. Let's connect all of them and see. Right. That's the sort of graph we get there. You can see that. It goes through the first point, last point, the middle two, very close. Slight deviation is there, but slight deviation, almost on the line. We need the gradient. Need 2 points. Where can I take 2 points? One could be this. This is at 6.75, isn't it? 1, 2, 3, 4, 6. No, not 6, 7. 7.5. 7.5 and 10.2. Then we have this point. This is 3 and 9.2. 3 and 9.2 is there. So let's take the gradient. Gradient is 1 over A rho, and the gradient 10.2 or 9.2 means 1. 7.5 minus 3.9 means 7.5 minus 3.5 means 3.6 equals. Oh wait, there is also a small issue in that it's in grams and centimeters. Grams and centimeters. So when you say delta y centimeter, let me convert that to meter. 3.6 is on the x-axis, which is grams. Let's convert to kilograms. Then it becomes meter and kilogram. 1 over A rho. How much was A? A was 4.5 into 10 to the power minus 4. 4.5 into 10 to the power minus 4 into rho. Let's bring rho up there. 10 to the power 3 minus 3 will come up as 10 to the power 3. 3.6 into 10 to the power 3 over 4.5. 4.5. 4. It's 5. 800. 800. Check whether the points are right. The points that we have taken, let's check that again. This is at 7.5 and 10.2. This is at, this is not 3.9, this is 3 and 9.2. Hold on, the points. Why I got this doubt is water can't be as low as 800 because water's density is around 1000. This is not 3.9. We get 3. So now you can say this is 1 over A gradient 10.2 minus 9.2, let's write it to avoid mistakes, over 7.5 minus 3, 1 over A rho. A, how much was A? 4.5 into 10 to the power minus 4. 4.5 into 10 to the power minus 4 into rho. So this is 4.5, this is 4.5, nicely it gets cancelled. Very nice, it gets cancelled. 10.2, 9.2, 1. Oh, we missed that centimeter and meter. This has to be multiplied by minus 2 because centimeters. This has to be multiplied by minus 3. So from this you get rho equals 10 to the power 3. Minus 2, minus 3, minus 1 remains. Minus 1, minus 4, minus 3 remains. Take it up, 3 kilogram per meter cube. Right? It's very nice. We have got 1000 itself. I'm not too sure whether the water would have had exactly 1000 because around 1000 is the value we have. Anyway, from the calculation, from the graph what we drew and get is 1000. Right? So you need to take 2 points. 2 points I took such that the graph goes through a vertical line and horizontal line. That's how I have chosen 2 points. So that the coordinates I use are perfect ones. No assumptions into that. So took those 2 values, find the gradient and then equate that to 1 over A rho. We already have A calculated there. Using all that we get rho equals 1000 kilogram per meter cube. Perfectly we are getting. Right? I did it for water, so I got this answer. You use it for a different one. Right? One more thing, at this point I have included the external diameter of tube. We have not shown you how we got that external diameter because in the experiment vernier caliper, we have spent some time and we have seen how to use the external jaws of vernier caliper and find the external diameter. We studied. So here I did not show you all that. I have taken the reading directly, 2.39 centimeter. I have read and I have taken it. So that's the value we have used here, and with all that, the answer we get 1000 kilogram per meter cube. Perfectly we are getting. These are experiments, you can have very minimal mistakes you can have. Errors are usually very low in these kind of experiments because, see, it's if at all only the measurement error, nothing else. No other error could be here. Because the setup is very simple. No complication. Understand? That's all in that experiment. Practice this very well. Now we are going to see few past paper questions on this experiment. Let's see how it has been tested so that in the future if we get questions, we know what kind of questions have been already tested. So let's take some past papers. Let's see the past paper questions that are from this experiment. This is from 2012 paper. A student has decided to measure the density of a stone with a smooth surface but having an irregular shape at home using the following items. A rectangular container, a 30 centimeter ruler, foot ruler with millimeter scale. Assume that he has access to the following items too. A household glass measuring cylinder capable of measuring liquid volumes up to nearest 5 milliliter. Electronic balance at a nearby retail shop. He started the experiment by determining the volume of container using the 30 centimeter ruler. What are the measurements he has to take? They said it's a rectangular container. Simple. So you need to get the length, width and height. Length, width, height. when an ordinary 30 centimeter ruler is used to take the above three measurements, one measurement may be less accurate. What is that measurement? What is the reason for that? Now see how you are going to have the rectangular container is something like this. Okay, this is how the container is going to look like. How will you keep the ruler? Look at it, your ruler. When you want to get the measurement on this side, you will keep like this. Say 0 here, let us say 0 is at this point. Okay, 0 here, and you get the point reading here, you get length measured. Similarly, if you want to get the width measured, you take the ruler, turn it, okay, keep it like this, okay, keep the 0 nearby. Right, keep it like this, where 0 is here, you can get the measurement. The problem is, or like, okay, if you want to get the internal measurements, now this is external, no, to get the capacity you have to get the internal measurements, right? Then what you do, you keep it here, keep it inside and get the measurements, yeah, right, keep this at 0, find the other reading. Similarly, this also, rather than getting the external reading, you get the internal reading, keep it like this here, this point is going to be 0, get the other reading here, then you will know the internal length and width. Then when you want to get the internal height of it, look at this, you take your ruler, and turn it vertically, you are going to keep it, you are going to keep it like this. Problem here, now look at this, where would the 0 be? 0 is going to be somewhere here. The meter ruler, 0 doesn't start from the end itself. From the end to 0 there is a gap, right? So from this is where 0 is going to be. And if you get the reading here, what will happen to this depth under 0? Do you understand? That under 0 part we will not be able to measure. So that's the difficulty we have here. So when earlier we said width, length and height, or you can say depth. So what is the measurement that has difficulty in measuring it? Depth. Why? The 0 mark of the ruler will not be at its end when ruler is kept vertically inside the container. There will be a gap between the base and a base of the container and the 0 mark of the ruler. Understand? So this can give you some challenges because he is not doing this experiment in the laboratory. Laboratory has meter rulers where 0 is marked at the end. But at home, when you just use a foot ruler, that wouldn't have those markings. Usually the 0 starts a little while, like a couple of millimeters after the end of the ruler. Next. He washed the stone thoroughly, dried it and kept it inside the container as shown in figure 1. Then he filled the remaining volume of the container up to the brim with a measured amount of water using the measuring cylinder. So he has filled it with water. It's filled, right? He knows the volume of water. Let's say VW is known. VW is known. He measured and he has filled it. Let the volume of water measured and added to the cylinder be V. It's not VW, let's put it as V. Okay, V. He knows the volume of water. Very simple. Now we can find the volume of the stone. Do you know why? We know the volume of the container also. We took the length, width and height. So we multiply all that, we can get the volume of the container. From the volume of the container, if you subtract the volume of water that we have filled in, the difference has to be the volume of this stone. Yeah, simple. Write down the expression for the volume of the stone in terms of V, x1, x2, x3. x1, x2, x3. When you multiply those through those three, you get the total volume of the container minus V. Minus V. If we have the option to choose a container with the same volume but having a narrow brim as shown in figure 2, explain as to why it is advantageous to select such a container. See, when the water level is in a, let's say this is a small tube, you will see a meniscus. Beaker also you will see a meniscus. Now look at these two. What we calculated as the container capacity is, look at this, what we calculated is this much. Let me use a different color. Okay, what we have actually calculated is up to this, the full amount, right? Let me draw a line. Right. But the water level is actually only up to here. Look at this. This is the water level. So the calculated level is up to here, but the actual water is here. This gap is the error. Right. You calculate x1, x2, x3, the total volume of the container, assuming that the top level of the water will be flat. But it won't be flat, it's a curve. It's a curve. So because of the curvature, there is going to be a small error in the volume. Similarly, here also. Here the error is going to be. Now look at this. When you use a narrow one, can you see the volume of error is less? Because the cross section is less, the curvature flat, the gap between those two is very less. That's why to get this volume correctly or volume closer to the water's volume, if you can use a narrower container, this error can be minimized. Right? So let's write this here. They are asking what is the advantage of using a narrower container. Let's write it here. The top level of water in the container will be a meniscus. Because of this, the volume of water will be less than the calculated volume, that is x1, x2, x3 of the container. This difference can be minimized or lowered, by using a container with smaller cross-sectional area. Clear? That's the reason why a narrower beaker or narrower container would have been better. What is the measurement that he should take in order to determine the density of the stone? He knows the volume. He needs the mass, because mass divided by volume is what you call density. Mass of the stone. mass of the stone. Hence, write down an expression for the density of stone in terms of symbols defined above. Mass of stone, let's write it as m. They have not given any any symbols for that. M divided by x1, x2, x3 minus b. Correct. This is the volume of stone. This is the mass of stone. Suppose you want to estimate the mass of huge rock that is situated on a flat land as shown in figure 3. It's a huge rock. See, this is the man's size and this is much bigger than the man. So, you can't take this the stone and put it in a container, won't work because it's a huge rock. As shown in figure 3, using the knowledge that you have gained from the above experiment. Assume that you have ability and provision to construct wooden boxes of any known volume or wooden structures of known size and access to sufficient quantity of fine sand instead of water. We are going to use the same idea here, right? What we will do, if you want to find the volume of the stone, we will construct a structure. What kind of structure? Look at this. Right. With the wooden box, maybe we don't need the top part of it. With a wooden box, we will make this structure. We don't need the top line. Let's erase it. Right. We will make a structure like this. So, basically the bottom also wouldn't come. Let's put it like this. One structure here. One structure here and another structure here. So, basically around the rock you make a wooden box shaped structure. The box, so you can measure the length, width and the height you can measure. Like we had earlier the rectangular container and a stone in it. The rectangular container is what I am making up around this stone, around this rock. Right, then what we have to do, we have to fill this. We have to fill this not with water, because if you pour water, water will be absorbed by the sand underneath. So, it shouldn't be water, must be the fine sand. Fine sand. Why they say fine sand is each and every small corners it can go and fill it. So, you fill this with fine sand. Then you know the total volume of the container. Fine sand also you can measure and fill it. So, you know the amount of or volume of fine sand that you have used. Get the difference, that has to be the volume of the rock. What kind of measuring device can be constructed to measure the volume of sand using the material given above? What kind of measuring device can be constructed to measure the volume of sand using the materials given above? See, based on the materials you have to make a small wooden box. Then you can measure the volume of it. And then, let's say, okay, one small wooden box which can have 2 meter cube of sand. Then every time you put one box of sand, 2 meter cube is put in, right? So, what you need here based on these materials given to you, we have to make a small wooden box of known volume. Like they have given when water was used in the first part of this experiment, they said you have a cup which can measure up to 5 milliliter. So, like every time you pour, 5 milliliter is what you are putting in. Likewise, something for the sand. Write down the major steps of a method that you would suggest in order to measure the volume of the rock. So, what we explained now, what do? We make a rectangular wooden box or wooden structure around the rock, fill it with fine sand, measuring the volume of it. Then, you find the volume of the wooden structure, subtract the volume of sand that we have filled in, that should give you the volume of rock. Construct construct a rectangular wooden block, a wooden structure, let's say, wooden structure around the rock and measure its internal length, width and the depth. Fill the structure with fine sand measuring the volume of sand used. The difference between the volume of wooden structure and the volume of fine sand is the volume of rock. So, more or less same method that we used for the small stone, but here we had to make a wooden structure and all that, right? What kind of measuring device can be constructed to measure the volume of sand using the materials given under A, D above? What kind of measuring device can be constructed? Now, sand, like earlier when we used water, they said you have some measuring cup which can measure up to 5 milliliter. So, we measure and put the water into the beaker or container. Now, we have to measure and put the sand into this structure. So, what do we do to measure sand? First, we have to make a smaller box, smaller wooden box. We can calculate the volume of it. So, we have to make a wooden box with known volume. Let's say one box has 1 meter cube volume. Then every time you fill a box of sand, you know you are using 1 meter cube volume, right? So, let's say a small wooden box with known volume, What is the other physical quantity that is needed to estimate the mass of the rock? We are going to estimate the mass of the rock. We know the volume of it. If you know the volume, to get the mass, what else do you need? Volume and mass, what's the connection? You know, density. Density equals mass by volume. So, to find the mass, if you know the density, then you can multiply density and volume, so that mass can be calculated. So, what's the other physical quantity that is needed? Density of the rock. Density of the rock. Density of the rock. Suggest a method to measure the quantity mentioned in D3 above. How do we measure the density? It's a big rock. What do? We just break a small piece from the rock, then it comes a small stone. And the first part of the experiment, we have seen how to find the density of a small stone. So, use the same procedure, you will get the density of it. Simple, right? Let's say, obtain a small piece of the rock. Basically, you just have to break the rock and take it, right? Use the method in part A, isn't it? Where did we use it? Part A. Yes, part A. To find the density of it. Only thing is, we have to assume the density is uniform throughout the rock. Right? Sometimes the rocks will not have uniform density. At some places it might be more dense, less dense. So, we take a sample from one part of it and we assume the density of that small sample is the same density throughout the rock, right. Another one, 2013. You are asked to determine the density of a given oil experimentally using Archimedes' principle. A setup consisting of a thin-walled glass test tube containing the oil and a transparent glass vessel with water as shown in the figure is provided to perform the experiment. The test tube floats in upright position in water as shown in the figure. A colored ring is clearly marked around the wall of the tube at P, and it can be used as the reference to measure heights. Following symbols are assigned to various parameters relevant to the setup, and use these symbols to answer the questions. Let's look at the setup. Right, this is the test tube. Right, this is where you have the ring, that's the point P, and then above that the height is what they measure as L1, L2. A is the area of cross section of the test tube above the ring, because below the ring the area is not uniform. Above the ring the cross section is uniform. Volume of the tube below the ring, V. This volume is V. L1 is the height of the oil column above the ring. You have put oil inside this, so the oil column above the ring is L1. Height of the water column above the ring is L2. L2. Mass of the empty test tube M. Density of the oil D. dW is the density of water. That's given. Write down an expression for the weight of the oil inside tube in terms of V, A, L1, D and G. So, what will happen here? The weight of the oil V, okay, so we will take the volume of oil and multiply by the density. Volume of oil has to be, the volume below the ring is V, above the ring I have to multiply by cross section and height. AL1 would be the volume here. So, the total volume is going to be V plus AL1 is the total volume of oil. Into D is the mass, volume into density is the mass. They are asking you to find the weight into G. This is what the weight, right. Let us say weight W equals this. Write down the expression for the total weight of the test tube with the oil. So, let us not call this W because they call something else as W, yes, right. Write down an expression for the total weight of W of the test tube with oil. What is the weight of test tube? Have they given that? Mass of the empty test tube is given. So, I can say total weight is going to be mass of empty test tube plus the weight of oil within that, right. Test tube's weight plus the weight of oil. Write down an expression for the upthrust acting on the test tube. Upthrust is the weight of water that has been displaced. So, you need to see how much of volume is immersed here. You can see V plus AL2, right. Up to here we have to get AL2. So, V plus AL2 is the volume of water that has been displaced into dWg, because weight of water that has been displaced is what you call upthrust. What relationship holds between W and U? Both have to be equal, then only the test tube will be in equilibrium, right. Weight of the test tube set and the upthrust have to be equal, W and U. In the relationship you have given in D1 above, arrange the parameters in W and U to obtain a relationship in the form L2 equals M L1 plus C. Right. So, V plus A L2 dWg, W was what? Mg plus V plus A L1 dg. Upthrust was equal to V plus AL2 dWg. This was the upthrust. Let us cancel G everywhere. Now, bring that here V plus AL2 equals, let me write this AL1D first, A D over dW L1, correct? Then let us write these two, M plus VD V into D over dW, correct? M is here, V into D is here, dW is down. Then V has to be subtracted there. Let us say L2 equals, A will divide this, so it will be D over dW into L1. Then V goes as minus V and the A is going to divide that. So, maybe I can take dW common base, M plus V D was already there, minus V with this dW minus V dW, and the A will come down, A, correct? That is what they ask. What is that? Or not here, I should have written on the other side, yes. So, here. So, L2 equals ML1, L2 equals, what did we get here? ML1, D over dW L1, or L2 equals ML1, this is M, plus C, the whole thing is C, M VD minus VDW over A, not, A dW, that is C. All of those are constants. M is the empty test tube's volume, mass, V is the volume of that test tube below the ring, D and dW are the densities, A is the cross section, all these are constants. So, you get Y equals mx plus C format. If a suitable graph is plotted using the relationship obtained D2 above, how would you determine the density of oil D using the graph? You need D, right? So, you take the gradient of the graph, that is going to be D over dW, right? Gradient of the graph, D over dW. So, D will be equal to dW over gradient, dW. D will be equal to dW into gradient, dW into gradient. Clear? So, basically the gradient gives you the relative density, multiply by density of water, you get density. Following measuring instruments are at your disposal: a half meter ruler, a vernier caliper and a travelling microscope. Of the given instruments, what is the most suitable instrument to measure L1 and L2? You are not allowed to change the position of the test tube. See, this is how you have it. You have a tube or beaker with water, inside that you have a test tube, there is a level here, there is a level here, then the water level here. You have to get these three, right? So like I need to get L1, L1 means I need to get this reading, this reading, this reading. The difference between these two will be L1, difference between these two will be L2. So, to get L1 and L2, what is the best suitable instrument to measure this without adjusting it, without taking it? Then if you can't take it, meter ruler, vernier caliper won't be helpful, because vernier caliper and meter ruler, you need to be able to hold what you measure, right? So, without touching at what you measure, if you want to get the measurements, it has to be travelling microscope, because without touching the apparatus, you can use travelling microscope and get the dimensions. How do you obtain relevant readings to measure L1 and L2 using the instrument that you have mentioned under E1? We have already seen how to use travelling microscope in the fourth experiment. We all know travelling microscope. So, what we have to do? First, focus on this ring. This is what they call P, ring P. So, once you get the clear picture, clear image of ring P, then get the vertical scales reading. then move it vertically, get the reading at L1 and L2. Yeah. So, let us write it. Focus the microscope on ring P and obtain the reading on vertical scale. Reading on vertical scale. First point. Second point, move the microscope vertically. So, let us say this is reading 1 vertically and focus on the meniscus of water column, or first the oil column, right, that comes first, oil column. Let the reading on, or obtain the reading, obtain the reading on vertical scale. Reading 2. Let us not go into too much of details of microscope. I do not have to say use that knob, this knob, don't use that knob, this knob. We can avoid all that because this is not a pure question on travelling microscope. Just in another question, how to use travelling microscope for a measurement is what they are asking. Don't go too much in detail, just briefly explain. Move the microscope vertically and focus on the meniscus of water column and obtain the reading on vertical scale. Let it be reading 3. So, what you call as L1 is the difference between reading 2 and reading 1. L2 is the difference between reading 3 and reading 1. Clear? That is how you get those readings using microscope. If the wall of the test tube is thick instead of thin, the corresponding expression for M in the expression that you have obtained in D2 above will yield M equals AID over AE dW. AI and AE are internal area of cross section and external area of cross section respectively of the tube above ring. To determine A1 and AE, what measurement do you have to take? AI and AE. AI is the internal area, so you need internal diameter and external diameter. How do you use proper instruments selected out of the measuring instruments given in E above to obtain the measurements? Internal diameter, external diameter, very comfortably you can measure with which one? Vernier caliper. It has internal jaws and external jaws. You can use them comfortably. Vernier caliper. Again vernier caliper. Right? Now 2016 on the same thing, same concept. 2012 you had a question, 2013 you had one, again in 2016 another one. When certain objects are packed in containers, they do not occupy the entire volume of the container. This occurs due to the shape of the objects, and under such situations a fraction of the container volume is always empty and filled with air. You can see the image where they have kept some balls. So in between balls, can you see the space like this? There are a lot of space like that which is empty. Empty means it's filled with air. Consider a container in the form of a cubical box of side length 8r, okay, which is fully packed with identical solid spheres of radius r in regular manner as shown in figure 1. This is called regular packing. So, if it is 8r, right, the diameter of one ball is 2r, 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 4 balls you can keep along the length, along the width and along the height. Find the number of spheres packed in the container. Very simple, like the scholarship questions, 4 into 4 into 4, grade 5 scholarship questions, 64, 64. Obtain an expression for the total material volume of all spheres packed in the container in terms of r and pi. So, it is going to be 4 by 3 pi r cubed is the volume of one container. You have 64 like that. So, that is 256 over 3 pi r cubed. 256 over 3 pi r cubed is the total volume of balls, the spheres that have been packed there. When the container is completely filled with spheres, total material volume of the spheres in the container volume of the fully packed container is called the packing fraction of the spheres. So, what they say, total material volume of the spheres in the container divided by volume of the fully packed container. See, if this is the container, so whatever you have packed is this much. The ratio between, let us say this is V1, container is V2, full capacity, V1 over V2 is what they say, what? Packing fraction, packing fraction. They just give a name for that, something new, we never heard of that, of spheres, and volume of the fully packed container is called the packed volume. V2 is the packed volume, correct? Find the packing fraction Fp for the above regular packing. Right, for this one, we know this is the materials volume that we have packed, 256 by 3 pi r cube, 256 by 3 pi r cube divided by full volume, it is a rectangular one, 8r, 8r, 8r. So, I can say 8r to the power 3. That will be r cube cancelled, 256 over 3 pi 8 cubed, 8, 8, 8. So, 8 into 8 is 64, 64 into 4 is 256, correct? So, you get pi by 6. If you replace pi by 22 by 7, so that is like 22 by 42, 11 by 21, 11 by 21, correct? That is the packing fraction, If m is the total mass of the spheres in the container, derive an expression for the ratio total mass of the matters divided by volume of the fully packed container in terms of m and r. This ratio is called the bulk density, This is, earlier we found volume to volume ratio, now we find mass to volume ratio, mass of the materials that are packed inside divided by the volume of the entire container. It is going to be m divided by 8r cubed. 8 cubed is 512. So, m over 512 r cubed. That is it, that is dB. What is the name for this one? dP, is it? Fp. Write down an expression for the density of the material of the spheres in terms of m, r, a, phi and l. Right, density, now see, density dm is mass divided by volume, mass is m. Volume 4 by 3 pi r cube into 64, right? 64 balls were there within the volume. So, the mass m is for all 64 balls. So, from this you get 3 will go up, 3m over 64 into 2 is 256, 64 into 4 pi r cube, 256 pi r cube. A student has decided to find parameters Fp, dB and dm for green gram using an experimental method. In this case, green gram is packed in a random manner. It is called random packing. See figure 2. The definitions mentioned in part C, this is figure 2, this is how it is packed. The definitions mentioned in part C, D and E for Fp, Fb and dm are valid for random packing of items of any shape too. First, he inserted dry green gram into a measuring cylinder and obtained a packed volume of 50 centimeter cube of green gram as shown in figure 2. Right, he got 50 centimeter cube of volume. Then he measured the mass of the packed volume 50 centimeter cube sample of green gram and it was 3.8 into 10 to the power minus 2 kilograms. That means 38 grams it is, 38 grams. Subsequently, he introduced the green gram sample into a measuring cylinder containing 50 centimeter cube of water and found that the water level raised to 82 centimeter mark. So, already there was 50 centimeter cube of water. In that he is putting all these green grams. So, you might expect, okay, there is 50 centimeter cube of water, 50 centimeter cube of grams, altogether it must be 100 centimeter cube, but it is not 100 centimeter cube, it is at 82. The reason is 50 centimeter cube of green grams, in between there would have been a lot of space. So, water will go into those space and fill as well, right. So, that is why it comes to 82. Now, what do they want? What is the material volume of green gram? Material volume of green gram. Now, look at this, out of this 50, I have to subtract the volume of air, right. So, let us say 50 minus, how much would be the air volume? Now, look at this, 50 and 50 should have been 100, but it is at 82. Where did that 18 centimeter cube of water go? 18 centimeter cube of water would have gone into the spaces here. That means the volume of spaces in between the grams should have been 18. That is why out of 50 centimeter cube of water, 18 has gone into these spaces, another 32 is on the top, correct. So, let us say 50 minus 18, 32 centimeter cube, 32 centimeter cube. Calculate the packing fraction Fp of the green gram. Fp, packing fraction 32 centimeter cube over 50 centimeter cube. It took 50 centimeter cube capacity, but actually the volume was only 32. You can say 0.64. Calculate the bulk density of green gram. Bulk density, that was mass divided by volume, isn't it? Where is that? dB. dB, bulk density, is mass divided by the volume of it. The mass of the matter is divided by volume of the fully packed container, yes. So, mass they said 38 grams, isn't it? 3.8 into 10 to the power minus 2. 3.8 into 10 to the power minus 2. 50 centimeter cube. This is kilogram. Centimeter cube, meter cube, correct. So, you get 3.8, or let us put it this way, 100 goes up, 380 over 50, 7.6 kilogram meter minus 3, kilogram per meter cube, 7.6 kilogram per meter cube, correct. Calculate the density of material of green gram in kilogram per meter cube. Density, the mass is 3.8 into 10 to the power minus 2, right? And the actual volume of it is only 32 centimeter cube. 32 centimeter cube, 1 centimeter is 10 to the power minus 2, cube will be 10 to the power minus 6. Wait, in the previous one also I will have to change it then. 10 to the power minus 6 it has to be. 10 to the power minus 6. Then it will be into 10 squared. So, it is going to be 760. right here. So, it is going to be let us say 10 to the power 4 goes up, 38 over 32 into 10 to the power 3 kilogram m minus 3, 19 by 16, that will be 1.31 14 by 16, 875. 1.1875 into 10 to the power 3 kilogram per meter cube. That is what the density is. The next one. A polythene bag is to be designed to pack 1 kilogram of green gram. Calculate the minimum volume of the bag needed. Right. So, see, we have this bulk ratio, bulk fraction or bulk density, which is m divided by V of the container, correct. We have already found the bulk density of this. Bulk density was 0.64, is it? No, 760 kilogram per meter cube. 760 kilogram per meter cube. So, it is meter cube. If I want to divide it to centimeter cube, I divide by 10 to the power 6. So, this is in kilogram per centimeter cube now. M is 1 kilogram, V. So, V has to be, look at this, 10 to the power 6 over 760 centimeter cube. That is 10 to the power 5 over 760. Let us say 100 over 76, 24, 8, 22, 12, 1. 1.31 into 10 to the power 3 centimeter cube. That is the volume of bag needed to pack 1 kilogram of green grams, right. So, this question has nothing much to do with any of the practicals that we have done, right, but the knowledges that we gained from experiments like the previous experiments we have done can be applied here, but more or less it is completely a new thing. So, once in a while, like once in a 5 years, 10 years, questions like this also come in the exam, right. You must be prepared to face that as well. Only thing is, if it comes like that, that is more easier, because since they are bringing something unrelated, they will give it easily. So, if you slowly, carefully read, paragraphs can be bigger, but when you read and do it, it is going to be much easier. You saw how easy it was, right. Cool. So, that is all in this experiment, the past paper questions that have come. Practice all this, try to understand yourself, right. If everything is okay, then let us move on to another experiment in the next session.